Welcome to the first section of the Beginning Docker video course. In this section, we are going to look at setting up Docker, how Docker works, some of the inbuilt Docker commands, and a comparison between VMs and Docker containers. In the first video, we are going to set up Docker in a VM that we can use in the rest of the course. Running Docker in a VM means we don't have to worry about our host platform, since Docker is currently a Linux-only technology. For ease of use, we're going to use Vagrant to manage the VM. This lets us easily control it from the command line. First, we need to install Vagrant. You can get Vagrant from their website at vagrantup.com. Just click on the Downloads and select your platform. If you have Vagrant installed already, you might want to upgrade. For example, if you installed it with Ruby Gems, you probably have an old version. Be sure to uninstall the Ruby Gem version to avoid conflict with the new version. Once it's installed, let's go to our terminal and create a new directory for our projects. This directory will be associated with the Docker VM. I've created a directory called Docker. Now inside this directory, we are going to run Vagrant init, passing it the name of a predefined Ubuntu image that has Docker and its dependencies. We've run Vagrant up to download the VM image and start the VM. This may take a while depending on your internet connection. We can test our VM by connecting via SSH. Vagrant comes with a command that makes this easy, called vagrant SSH. Running it in this directory will use the VM that we initialized it in. Inside the VM, let's run Docker version to make sure it's installed. If we want, we can also run apt-get update and update the Docker in case there is a newer version. After exiting the VM, we can then run vagrant halt to stop the VM, which will free up the memory and CPU it takes to run. Running vagrant up again would start it. You now have Vagrant VM ready to play with Docker, and an easy way to get into it via the command line. In the next video, we're going to look at containers and how they compare to virtual machines. In our previous video, we set up a Docker environment inside a Vagrant VM. You've probably worked with virtual machines by now, either using a cloud provider like Amazon EC2 or a local VM manager like VMware or VirtualBox. So we're going to run through some basic examples of using Docker containers and compare that experience to using a virtual machine using VirtualBox via Vagrant. First, we're going to see how quick it is to get a bash shell in a container versus a virtual machine from nothing. First, using Vagrant. This will boot a VM and then SSH into it. Now let's get a bash shell in a container using Docker. You must have already noticed how quickly the container started up when compared to the VM. That's because a VM is emulating an entire hardware system to run its own operating system. Docker containers are just an isolated system environment run with the same kernel as the host. Let's time the difference between the two by displaying system distribution information. The difference is roughly 300 times faster starting a container than a VM on this machine. It's effectively instantaneous. The next difference we will illustrate is how VMs generally run an entire init system, running a system of processes just to operate. This includes cron, NTPD, syslog, and many other support services that are generally needed when running a machine. But Docker containers are for running a single process. It may have children processes, but inside the container, it's as if your process is the root process. So a VM is about an entire system of processes, many of which you don't even care about, whereas a container is going to be just about the process you want to run. Combined with all the hardware emulation that's happening, this makes VMs extremely heavyweight, especially for running a few simple tasks or a single daemon. Lastly, let's see how this affects our workflow. Compared to the VM images, container images are extremely easy to author and modify. Very often, we can just run bash in a container, customize, exit, and commit, a process that can be done in under 30 seconds. Whereas a VM, it will take at least 30 seconds to start, then often much longer to take a snapshot. Here, we just took an existing image, modified it, and made a new one, then ran it, probably in the less time it would take to finish taking a VM snapshot in many cases. Just to rub it in VM's face, let's instantly run 3 more of this container. That was quick, and they're all serving up our page. If we wanted to do that with 3 VMs, well, my laptop wouldn't be able to run 3 VMs. So, to summarize, like VMs, you can put everything an application needs inside a container, but containers are extremely lightweight. The difference has a qualitative effect on your workflow and what you can use them for. In the next video, we'll take a look at the core Docker objects and how Docker works at an architectural and conceptual level. In our previous video, we saw how containers differ from virtual machines. Before we dive into Docker commands, we'll use this video to quickly summarize the concepts behind Docker. First, we'll review the main objects that Docker interacts with. Images. Like VMs, container images are templates for containers. They consist mostly of a file system, but also metadata about a container, including how it should operate by default. If you wanted to move or share a container, you do so by making an image or a snapshot of it, sharing the image using Docker commands. Docker manages images on a host and gives you the tools to transport them across hosts, usually via registries. Containers. Containers are instances of images, basically copies, that then run an isolated process inside them. To the process, it looks as if it has its own system based on the file system of the image. It can change the file system, but any changes have to be committed back to an image to persist. Docker manages containers like processes, meaning you can start, stop, run in the background, run interactively, etc. Docker files. Docker files are build files that instruct Docker how to consistently build and configure a container image. Registries. Registries serve images you can pull from and push into from Docker. The Docker index is considered the main public registry. Docker files and registries we'll learn about as we go. The two important concepts are images and containers. When you start a container, it's always based on an image. However, the image file system is not actually copied. Docker containers use a layered copy-on-write file system. This means the files you see in a container when it starts are actually the files in the image file system until a change is made. Changes made in the container collectively make up a layer and can be committed to an image. Images are just a collection of layers or file system changes. This allows Docker to be efficient with disk space. It's also why registries are important, since they're aware of layers and can only send the layers you don't have when you pull an image. Containers are not just a file system. They always run with a command. This command process is run in isolation using kernel namespacing and C groups. This not only sandboxes the process, but lets us specify resource limitations for the process. This is classically known as Linux containerization, or LXC, which is where the name container originally comes from. However, Docker containers are much more than Linux containers. While Linux containers focus on process isolation, Docker containers build on this and provide a high-level tooling for a more portable, higher-level container. Some call this an application container, but we just call them Docker containers. We now know Docker containers and images, the most important concepts in Docker. We have an idea of Docker files and registries, but these will be explained in more detail in later videos. In section 2, we'll look at running containerized commands, making changes to containers, and working with the Docker index. Welcome to Beginning Docker, a video course by Pact Publishing. My name is Paul Bailey, and I will be the voiceover for Donald Simpson. Donald Simpson is an information technology consultant. He has over 15 years of experience in programming, build management, and process automation. He has worked with a wide variety of multinational companies to develop bespoke automated solutions using Docker and virtualization technologies. One of the major challenges while creating an application is adapting your application to run smoothly on the entire plethora of operating systems available. Docker is an extremely efficient technology that allows you to wrap all your code along with its supporting files into a single bundle. Our Docker journey starts with an introduction to the basics, moving on to the key commands you need to know to work with Docker. It also covers some practical examples which put our learning into practice by building our own application, packaging it, and then deploying it as well. Section 1 deals with the fundamentals of Docker, explaining how it works, how to set it up, and how to get started on leveraging the benefits of this technology. We are going to set up Docker in a VM that we can use in the rest of the course. In section 2, we are going to familiarize ourselves with basic Docker commands and workflow. Since the real meat of Docker is running commands inside containers, that's where we'll be starting. In section 3, we'll be learning how to programmatically make or build container images. We'll also learn about Docker files and see a detailed overview of container management. In section 4, we're going to revisit the Docker run command and explore some of the features it provides when running containerized commands. In section 5, we're going to be building and deploying a simple web application using Docker. This will be pretty interesting. In the last section, we will familiarize ourselves with Docker Remote API. We will also explore the idea of automation and tooling around Docker. This course assumes basic knowledge of Linux, but supplies everything you need to know to get your own Docker environment up and running. So let's dive in. In the previous section, we set up Docker in Vagrant VM, compared the containers with virtual machines, and took a look at how Docker and containers work. In this section, we are going to familiarize ourselves with basic Docker commands and workflow. Since the real meat of Docker is running commands inside containers, that's where we'll be starting. In this video, we'll be using these commands, primarily focusing on Docker run. Containers are ultimately about running a process. Docker provides many ways to run commands in containers, so we'll explore 3 basic ways in which you can run commands. Running commands in the foreground, running interactive commands in the foreground, running long-running commands in the background. First, let's simply run the is command in a container to see what happens. We'll use the standard Ubuntu container image for all these examples. What you should see is a listing of the root directory inside the container. After this is run, the container has stopped since the process has ended. We can see the container is still around by using Docker PS-A. This will show us all the containers around, even those that aren't running. Since we don't want to do anything with this container now that it's finished, we should remove it using Docker rm. In another basic run example, we'll ping Google. This time, we'll run with the --rm to automatically remove it when it's done. The ping is not your system ping. It's the ping inside the container, isolated from your host system. Running long-running commands like this can be closed the same way it would normally outside of Docker with Ctrl+C. Here let's try to run the Vim text editor. As you can see, it can't find Vim in this container. We'll have to install it with apt-get. It aborted. Why? It wanted confirmation input from us, but we were not running the command interactively, so let's do that next. Interactive commands are generally run with 2 options, -i, which is interactive, though technically it means it won't close standard in. Then we use -t, which emulates a text terminal. This way, the command operates more like it would normally in your terminal. For example, if we wanted to run bash in our container, we'd use these options. Now when we run our apt-get command, it takes our confirmation input. But as you might realize, this command is somewhat pointless if our container is removed after it finishes installing Vim. We'll address this in the next video, but for now, we can run a more complex command that will install Vim and then run it. This runs bash in the container with a compound command. The && operator wouldn't work otherwise, since it would be interpreted by our host shell environment. After we exit the program, we also exit the container, and the container gets cleaned up. Lastly, we're going to run a command in the background. You can actually do this with any command, as it just means we won't be attaching to the process, but this is frequently done for daemon processes that run a server. This last example is a fairly complicated compound command, since we're going to install, set up, and run the OpenSSH server. We're also using the port mapping option since we want to connect to the SSH server. Unlike when running in the foreground, running in detached mode returns the container ID. We can then use this in other commands to interact with the container. For example, to see the output so far, we can use docker logs. But now, let's try connecting to our containerized SSH server. We just SSH'd into our container. We can run commands here as if we ran bash in the foreground like before. Any commands here will be subprocesses of our containerized command and will also be isolated in the container. Since our command is running indefinitely in detached mode, we have to explicitly stop it. We're going to use docker kill to do this, since our command is not one that will close cleanly with docker stop. Lastly, we'll have to manually clean it up. In this video, we learned how to run commands using docker run, as well as some supporting commands. We saw how to run basic foreground commands, interactive commands with a sudo terminal, and even how to run a daemon process in the background. These workflows are core foundation of using Docker. In the next video, we'll introduce a new set of commands that are used for managing your containers. In the previous video, we saw a number of ways to create and start containers. Once you've started them, there are various commands you have to manage them. You were already introduced to a few, but let's look at some more of them. In this video, we'll be introducing these commands. Don't be intimidated, most of these are very simple commands. Managing containers is mostly a matter of managing processes, but in a way that is container aware. Docker provides a suite of utilities to manage container processes in much the same way you would regular processes. We're going to see how you can inspect containers, see their logs, stop them, and ultimately remove them. Let's begin by starting a couple of containers that will stick around doing pointless work. Ping will work well. We can see all the running containers with Docker PaaS. This shows relevant information about the containers, the most useful of which is the container ID, which we can use with other commands. However, you might also notice the names generated for each container. You can also use this human-friendly name to refer to a container, and you can even set this friendly name by using the --" name flag with docker run. One frequently used flag of Docker PaaS is a -a, which shows all containers, including containers that have stopped. We can use the IDs listed to get more information about the container, running or not. For example, we can take any container and inspect it with docker inspect. This gives us a JSON data structure of the state of that container. Take a look and see what kind of information is associated with a container. Again, we can also inspect a container by its name, like this. Let's dig deeper into these processes. We can see the output of any container, running or not, using Docker logs. If it's a running container, we can follow the logs live as if we were using tail -f, using the -f flag. Docker logs lets you see process output, but if you want to interact with a detached container process, you want to attach it using docker attach. This is a more advanced command, so I'll let you explore it on your own. However, be careful. If you don't use it correctly, you can lock up your terminal. As a brief diversion, checking and copying the container ID can be a bit annoying. Names make it a little easier. But here is a quick trick to work with the last container you made. Let's make a detached container. This will return the full container ID. But we don't even need to bother with that, because we can run a variant of Docker PaaS to get the ID of the last container we made. Just use the -l flag to only show the last container, and -q to only show the ID of the containers. We can use this as a subcommand in, for example, getting logs. When your container processes don't end by themselves, you can stop them with docker stop. By default, it will try to stop with a sig term. but then after a timeout, kill it with sig kill. I'm usually more forceful, so I often skip docker stop and use docker kill. Now, if we look at our Docker PS, we don't have any running containers. But if we run docker ps -a, we can see they're still around. They're not running, but their file systems and metadata exists. This can be useful for inspecting logs after you've stopped the process. If you don't run commands with the -rm option or run a lot of detached processes, you'll end up with a lot of stopped containers sitting around. You can delete them individually with docker rm. But if ever you want to just clear them all out, including running containers, we can use docker ps -aq, which lists all container IDs, with xargs to call docker rm-f for each ID, like this. We now have no running or stopped containers listed. To wrap up, we've learned all the basic commands for working with the process aspect of containers. We can now start, list, stop, inspect, follow logs, and remove your containers. In the next video, we'll be looking at 3 new commands that can be used to make changes to a container image. In our last videos, we learned how to start and manage containers. You may have noticed every time we ran a container, it started from the same point or image. None of our changes to the file system stayed with that image. In this video, we're going to use these new commands to learn how to make changes to a container image. Often, you want to work with containers that are already set up the way you want, instead of setting them up from scratch every time. Perhaps you want to have it configured a certain way or have certain applications installed. Here we're going to create an image made to run an SSH server. To do this, we'll make a custom container image based on the stock Ubuntu image. Let's start by seeing what images we have with Docker images. Whenever you try to run a container based on an image you don't have, it's downloaded automatically, so you may see a few. Since we've been using the Ubuntu image, you should see Ubuntu listed here like I do. To make a new image, we start by running a container to make the changes we want. Using bash is the easiest way to make changes interactively. So we just need to start a container running bash. Let's check to ensure the SSH server hasn't been installed yet. Okay, before we install anything, let's update our apt-get repositories. This will ensure we're working with the latest packages. Now let's install the Open SSH server package with apt-get. We use a full path because SSHD is particular about how we start it. Looks like it needs a directory created. When we ran it in the previous video, we had to create this directory in the same compound command we used to start SSHD because the container didn't have it. Making it now will ensure it's there in the image we'll make. If you recall, we also had to set a password for the root user since we'll be connecting as root and SSH will ask for a password. Let's set that here. We also need to update the SSHD config file to allow root to log in, and another small change to allow authentication to work. That's all the changes we'll make, so let's exit. The container is now stopped, but it's still around with its changes. We can inspect the changes to the file system using docker diff. This shows us exactly what files were changed after installing Open SSH Server and running those commands inside the container. Let's run this through less so we can look through it more easily. You can see it installed a number of files all over the place. This is normally what happens when you install software, and it's actually kind of nice that Docker allows us to see this easily. To persist our changes to an image, we use docker commit with a container ID and an image name. The common convention is to use a unique username / image name. You'll see why we do this in a later video. Now let's start SSHD in a container from this new image. Remember, we have to open port 22 in order to be able to connect to it. Then we'll connect to it. So it works. But lastly, when you commit a container to an image, it also remembers the last run parameters you used by default. If we commit again with this last container, the next time we won't need to specify the SSHD command or that it needs port 22, since it will have already learned that from this container. Okay, now we can clean up the container. As you can see, this workflow is very simple, making it very easy to create new container images. You can do it over and over again to customize or fork container images, however you like. In the next video, we'll take a look at ways to share your change containers with other hosts and the rest of the world. In the previous video, we saw how to create our own container images. This video will show us how to share them with the world, which also makes it convenient for you to access them from other hosts. These are the new commands we'll be using. Docker registries are servers that store Docker images in a way that's layer-aware and efficient. There's a free public registry run by the company behind Docker, called the Docker Hub. We can upload and download images from this index as an easy way to share and move containers around. We need to register an account with the Docker website before we can upload anything to the hub. Visit docker.io and click the sign up link. Now we authenticate with Docker on the command line. Simply run docker login and provide the credentials you just set up. Okay, that was easy. Next step. Remember, we can run Docker images to see what images we have on this host. We previously made an SSHD container image, so let's put that online. I named mine Donald Simpson /SSHD, which begins with my Docker username. This is the convention you need to follow for pushing to the Docker index. If you registered a username that isn't the username you used in your image name, we'll have to recommit it. To recommit, just run a container with the old image name, then commit to a new image, new. For me, I'm just going to add example to the end of my image name. Now we can push with Docker push. You'll see it's only uploading layers it doesn't know about. Since we built it with Ubuntu image from this repository, it's not uploading any of that, just the changes we made. Now, if we visit the Docker index website and log in, we can see our uploaded container image. We should test it to make sure it works. First, we'll have to delete the image on our host. We can do this with docker rmi, not to be confused with docker rm. This command is for removing images. Make sure you don't have any containers running with this image first. Now, let's pull the image from the index. Normally, we don't need to run pull, because if you try to run a container with an image you don't have, it'll automatically pull the image. However, it can be useful to do this step up front. And we can run it. We still have to specify which host port we want to use to reach the internal port 22. But you can see, we don't need to specify the command since we configured it with a default. We're going to use a slightly different one this time. We can connect it via port 2223. And it works. Again, we clean up. That was pretty easy. Now your image is public and anybody else can use it. There are other ways to move containers around if you don't want to make it public, but we'll save that for later. In the next video, we'll look at how you can use the Docker index to find and use third-party containers. In our previous video, we saw how to use the public hub for sharing your container images. To finish this section, we're going to go through the process of using the hub to find and use a third-party container. Part of the beauty of Docker is that it makes shipping around software very easy. A Docker container has all its system dependencies inside it. and you can run it on any host system with Docker. This makes it ideal for sharing pre-configured open source software. We're going to walk through finding and using existing Dockerized software. In this case, the data store Redis. We want a Redis container to run. So where do we start? Well, there's actually a Docker search command that will search against the public index. However, I found this is not a great tool to find something new. To start with, if I picked any of the search results, I wouldn't know how to use them. There's no docs. That's why I always start with the Docker help website. So let's go there. Here, we get what looks like similar, if not the exact same results, but we can learn much more about them. Unfortunately, many of them have no descriptions or useful information. The ones that will, however, are marked as official. These are images that were built automatically from a linked GitHub repo. This ensures that we can see the source for the container image, which often also includes documentation. The first in the list is an official build. We can see it actually has a good description and instructions. What's more is we can click on a link to the repository. This image is part of a project called the Docker File Project. This is an open source project that contains Docker files for popular open source projects that are then submitted as official builds on the Docker Hub. Although it's still young, this is likely the best place to find solid Docker containers for off-the-shelf open source software. Lucky for us, they have Redis in their catalog. Now that we know what we want to pull from the hub, we can just pull it down. After some quick reading, it looks like the running container will run the Redis server command by default and listen on port 6379. So let's run a container with that port open. We'll also give it a friendly name of Redis. Now, let's just peek at the logs to see that everything went okay. Alright, we've downloaded and run Redis using Docker. It looks like we can use this container image to run the client, so we don't even have to install a Redis client to test our Redis server. This command is using some advanced Docker run features, including linking and entry point overriding. We'll explore these in future videos. For now, just run it exactly as I do. We're in a Redis shell. We can set a value and get to see it's actually talking with the server. Success! Let's exit. Although you may have to do some digging to make sure you know what you're getting, finding Dockerized open source software is quite fun. It's also valuable in seeing how they've containerized various projects, which we'll be doing in the next section. Welcome to the third section of the course. In the previous section, we looked at managing, finding, and working with containers. In this section, we'll be learning how to programmatically make or build container images. In this video, we're going to introduce you to the Docker file. Manually, interactively making containers can be a pain, especially if you need to do it often or in multiple places. Docker addresses this by providing a Docker file format that lets you define how to make a Docker container. Docker can then build a container from that file in the same way, no matter what environment. Let's do this with our SSH server container from before. When we make a Docker file, it's best to create it inside a directory. This is often the project directory for the container. It's important to do this because of various conventions in the Docker ecosystem we'll learn about later. So to start, let's create a directory for our new Docker image project. Inside, we'll make a file called Dockerfile. You can name it anything, but it makes more sense to name it Dockerfile so people know what it is and to follow conventions used by other tooling. We'll edit the Docker file with Vim. The format of the Docker file is simple. It's simply a list of instructions, like a script. Each instruction has a keyword in all capital letters. The first one we'll use is from. From always goes at the top of the file, and we use it to specify the base image we want to use for this container. Here we'll use Ubuntu as we have been. Under From, it's best practice to specify an author or owner of this container using the maintainer instruction. It takes a name and email address in standard email format. Now the interesting instructions. The main instruction is run. This is the equivalent of us loading bash and interactively running a command. Here I'm running two commands in one. I do this to group significant operations into the same layer, since each run instruction produces a new layer. I'll also make the /var/run directory SSH needs. There are other instructions, but we'll explore them in future videos. Now we can build this Docker file using the docker build command. It takes the path or URL of the project directory containing a Docker file. Hence the importance of naming it Docker file and having it in a directory. When the Docker build finishes, it will have produced an image, but it won't have a name, just an ID. So we usually always use the -t option of Docker build to specify an image repository name to use with the resulting image. Then, as I said before, we pass it in the path to the Docker file project, in this case, the current directory. As you can see now, we have an image that has the SSH server package installed. Docker file makes an already quick process even quicker and introduces the concept of source files for containers. We'll expand on this concept as the section progresses. In the next video, we'll examine how to add files to your new container. In the last video, we saw how to build Docker files using container images using the run instruction. Now we'll see how to use the add instruction to add files to a container image. Please remember that if you would like to find out more about any of the commands we are looking at, the online Docker manual is a great place to start. When making container images, you don't always want to run commands, but edit files, often configuration files. Since it's best to practice to version these files, we want to keep them in the source for our container project. But how do we get them into the container? We simply use the add instruction in Dockerfile. We're back to our SSH server container project directory. You can see we have the Docker file from the last video. We're going to keep the SSHD configuration in this project and add it to the container we built. So to start, let's get the default configuration. We might as well get it from our container simply by running cat and piping it into a file. As you can see, we now have a copy of the default SSHD config file here in our directory. For demo's sake, let's just change the port from 22 to 2222. Now that we have a file that we want to include in our container image, we can use the add instruction in our Docker file to add the file. The first argument of add is the source path, which is relative to the project directory at build time. The second argument is the full path to the destination. It's sort of like the copy command, except it does have some interesting characteristics. For example, the source could be a URL, which would then be downloaded and placed at the destination argument. You'll want to check the docs for advanced add semantics. But often, you'll use it this way. Now we can rebuild the image using docker build, as we did last time. Then, we'll just go into a new container and inspect the SSHD config file. There's our port change. So this is the file from our project directory. You can easily include files from your project directory into your container image. This is perfect for configuration files or other artifacts. And remember, you can add entire directories or even downloaded files over HTTP. In the next video, we'll look at affecting containers beyond the file system and altering how they are used. In the last videos, we learned how to use Docker files to automate the build process of making container images. Now we're going to see how we can use Docker files to affect containers beyond the file system. Docker containers are about running processes, but there are many properties of the environment that affect the processes including what the user is running as, environment variables, and its access to the network. We can use Docker files to specify this extra information about how container processes should be run. First, there are two instructions that affect what is run. When you run a container, you can specify the command to run. But you don't have to if there is a default command on the container. The cmd instruction lets us specify this. Back in our SSH server container project directory, we can open our Docker file and add the command instruction to run the SSHD daemon by default. Now, after we have built this Docker file, we'll be able to run an SSHD container with no command. There it is running SSHD. We'll stop it for now. The other instruction affecting what processes run is entry point. It can be used to achieve the same effect as command, but using entry point, you can't specify a different command without using a special flag in Docker run. Instead, the command passed in Docker run will be appended to the entry point command, making the container a little more locked into a particular command. Here, I passed -8 as the command to run, which is being appended to the entry point command. If I want to run anything other than SSHD, I have to go more out of my as a user for this container. So normally we should use command instead of entry point, unless you really know what you're doing. Now, while we're in this Docker file, let's add some instructions that will affect the environment of the process. First, I'm going to set the user commands will run as. This is significant because by default they run as root. Here we'll run as the nobody user. Next, we'll set the working directory to /tmp. Lastly, we're going to set an environment variable just to see how we can do it. Now, let's run a few commands in this container to see the effect of our instructions. First, the user ID we can see isn't root, it's the nobody user. Next, the current working directory when running a command we can see is /tmp. Lastly, if we show the environment inside the container, we can see our foobar hello world value. There is one more instruction to cover here, which is the expose instruction. This tells Docker that this container is going to be running a daemon that's listening on a particular port. Since container run in an isolated network, in order for a container process to accept connections, Docker must forward a port. We've been doing this with the -p argument of Docker run. We'll always have to do this, but it's useful to know that a container will be listening on a port, so we can provide that metadata using expose. We'll expose 2222, since that's what we set the SSHD config to use previously. The internal port is not actually important, since we'll only ever access it via a port specified when using Docker run. We'll run the container now, even when we don't use -p to open a port. We can see with Docker PS that this container is exposing TCP port 2222. To summarize, we can use Dockerfile instructions to affect how users ultimately use the container, including what command it runs and how it runs. In the next video, we'll take a look at ways in which we can build upon and reuse existing Docker containers. Now that we're comfortable using Docker files to build basic container images, we can learn how to build off existing Dockerfile built projects. Let's do that in this video. Say we have our SSH server container, but we want a separate custom version of it. We can build a new container project directory with its own Docker file based on the previously made container image. And we can even encourage this behavior in our original Docker file. We'll see what I mean in a moment. Let's create a new project directory. Inside, we'll make a new Docker file. It's based off our SSHD example image, so we can use that in the from instruction. Again, I'm going to be the maintainer, or in your case, you would be. Now, if we run instructions, they'll happen on top of the Donald Simpson /SSHD example image, and if we add metadata instructions, they'll override the previous values. That's what we'll focus on here. We'll make this container run as root. Now we build it and check the user. But now, what if we wanted to customize the SSHD config? Well, we can add another add instruction to add our own config on top of the previous one. However, another interesting approach is to use the onBuild meta instruction in the upstream container. What this does is tells Docker build to always run this add instruction when building, even if it's building a downstream container image. This way, the upstream container can specify how, for example, you customize configuration. We build this container again and head back to our new container project. We'll copy the configuration over on the way. Now, if we build this project, it will include the add instruction, even though this Docker file doesn't have one. As you can see, the Docker ecosystem is made to build off each other's images, and even Dockerfile supports mechanisms to support these concepts. The next video takes a look at trusted builds, what they are, why you may want to use them, and how to set them up. Throughout this section, we've seen how to automate the build process for Docker containers. Now we see how this is used to provide automated builds on the Docker Hub. As we've seen before, we're more likely to use containers from the hub that are marked as automated builds, since it means we can see how it was built and ensure that what we're downloading was built from that source. If we want our images to take advantage of this, we just have to make a public GitHub repository and set up an automated build. If you don't have one already, you'll need a GitHub user account. You can sign up for free at github.com. On GitHub, you'll want to create a new repository for your container project. I've already made one here. It's empty. So we'll need to push our source to GitHub. Let's go to our project directory and initialize Git. And we'll grab the command to set up the GitHub remote. Now, just add our files, commit, and push. Now we should see our files on GitHub. Great! Now if we go to the Docker index and log in, we can link our GitHub account to our Docker account. My account is already linked, but to link, all you have to do is to use authorize Docker index to access your GitHub account via OAuth. Now that we're linked and our repository is set up, we can create an automated build. If we click Add Automated Build, we'll get a list of our repositories. Find the one we created and click Select. Most of the default settings are fine. However, be sure you don't have an existing image on the index with the name of this automated build. We pushed one previously, but I've since deleted it, so I can create an automated build with the same name. Now it's going to build the container on the Docker I/O servers. This is one of the benefits of having a standard Docker file to describe how to build Docker containers. Once it's done building, we can see our image on the index, with all the extra information about it being an automated build, including a link to our GitHub repository. One of the nice features of automated builds is that now your repository is linked to the index. Whenever you push your changes to your container project in GitHub, it will automatically trigger a build and update the image on the hub. You never have to push to hub again. Automated builds are probably the ideal way to share images publicly. So if you want to create reusable containers for others, this is the ideal workflow. In this section, we have learned about Docker files and looked in detail at container management, working with containers, building upon them, and setting up our own trusted containers. In the next section, we look at Docker defaults, ports, and networking with Docker, and examine ways in which we can link containers together. Welcome to the first video of Section 4. In the previous section, we looked at making and building our own container images. In this section, we're going to revisit the docker run command and explore some of the features it provides us when running containerized commands. To start, we're going to look at its ability to limit resource usage. Running many containers on the same host means they share resources, despite being in isolated environments. In order for them to live happily together, Docker allows us to set CPU priority and memory limitations. We can set these at runtime using arguments of docker run. First, let's look at the ability to prioritize CPU to certain container processes. To make this clear, we're going to be using a container called prime sum, which will calculate the sum of all prime numbers up to a given amount. It's a simple way to demonstrate some kind of long-running CPU-intensive task. Get it with docker pull Donald Simpson /primesum. Let's see what happens when we run it. The argument 3000 means run until it's summed 3000 prime numbers, starting from 1. You can see, once it finishes, it displays how long it took to run. Let's run a few in the background so we can see what it's like when multiple container processes compete for CPU. Since the first one starts with the least competition, let's look at the last container, since it ran while there was the most competition. It took much longer than when we ran it alone. However, if we were to prioritize its CPU usage, we would get it to finish much quicker, at least compared to the others. We'll run it once by itself with priority, so we can use our command history to quickly run it as the fifth process. The value of the C argument is going to be a relative weight, so the specific value depends on what value you give into other processes. Okay, now let's run 5 prime sums again, with the last one having priority. Looking at the logs. Now we're going to look at limiting memory usage. This works differently than CPU, in that we can specify a maximum amount of memory that can be used before the process is killed. Again, I have pre-made container and demonstrated this. Let's pull it. It's called Donald Simpson /memalloc. This tool lets us allocate and also use memory up to a specific amount specified in megabytes. If we run it with one argument, it will allocate that amount in memory and wait for us to exit. Specifying a second argument will actually use this memory. We have this because Docker limitation only works against used memory, not allocated. So let's try it without limitation. Allocating and using 256 megabytes. This time we're going to run detached so we can inspect its usage. Using px-awks, we can find the process and see its memory usage in kilobytes. Here we can see it's using at least 256 megabytes, since the program runtime also uses some memory. Okay, let's stop that process. Now let's run the same experiment using a memory limit. The docker run-m argument lets us specify an amount in various units. Here, we'll use m for megabytes and limit it to 256 megabytes. We're going to run it in the foreground this time. We can see it allocated memory, but when it went to use it up, it was killed once it reached 256. We can see in Docker PS it has exited. These mechanisms are a convenience of Docker to let you allocate or limit certain system resources to containers. In the next video, we'll be taking a look at how to use Docker Run to override default settings. In the last video, we saw how to use Docker Run to limit resource usage for containers. Here, we're going to see how to use Docker Run to override some of the defaults that come with the containers, usually specified from their Docker files. Once you start using third-party containers, you may find that their container is more limiting than helpful to you. Luckily, many of the settings you can specify in Docker files can be overridden with Docker Run arguments. In the last video, we used a container called memalloc. It was made to run one executable binary in that image. So I set the entry point instruction in the Docker file. This had the effect that if I ran the container with no command, it would run that executable. And if I specified a command, it would use those as arguments to the executable. But what if I wanted to poke around inside the container using a shell? Well, we can do that easily by overriding the entry point to use bin sh instead. Now we're inside the container using a shell. Perhaps not how it was intended to be used, but possible nonetheless. We can see that the busy box was used as the base image for this container, which is why it's so small. Another useful, maybe more important parameter to override is what the user containerized process runs as. By default, the user is root. However, it's good practice not to use root since there are limitations, and sometimes unknown bugs in the isolation technologies used that could be vulnerable to attack. So to be safer, we can run a container process overriding the user it will run as by passing in a -u equals username arg. Now our container process is running as the nobody user. Just be sure the user exists in the container system. For example, the busybox image doesn't have a John user, so if we ran busybox, we would not be able to run as John. But probably the most used override setting is environment variables. It's not common for containers to set special environment variables since they're most useful being set when you run a containerized command. However, if a container did specify default environment variables, this method will override them. We'll just run Ubuntu bash and see what the environment looks like. Okay, now let's set our own environment variables. We can use one or more -e arguments like this. There they are. If you have a lot of variables, you can create a file full of key value arguments on their own lines and load them with -env -file argument. There are other defaults you can override with Docker run, and you can explore them all with Docker run -h. In the next videos, we'll continue to explore a few of the more useful ones. In the previous video, we looked at overriding defaults with Docker run. In this video, we're going to look at Docker volumes and mounts, and how we can use Docker run to configure them for our containers. When you start using Docker for applications, such as databases, variable runtime state is something to consider. So far, most of our data management has been around setting up system images as environments to run processes. But the job of a process is to use and manage lots of data. We don't want it to be part of the container. Instead, we use mounts and volumes. Docker run has a -v flag, which lets us set up data volumes that are mounted inside our container. The simplest example of this, mounting part of our host file system inside of a container. Here I have a directory on my host system. It's got a file here already called host file, which just has the contents hello from the host file system. We can mount this directory inside a container when we run it using the -v flag. The value is the host location, the location to mount it inside the container. We'll simply put it in /mnt. There's our files. We can read them. We can also write new ones. When we exit back to this directory from the host system, we can see the new file we made and its contents. By default, these mounts are read-write, but if you check the documentation, you can see how you can easily make a read-only mount inside your containers. Docker also introduces the concept of volumes, which are basically directories of the host system managed by Docker. These are even easier to set up, since you don't need to pick a directory of the host system. Although they're available on the host system, they're intended to mostly be used from and across containers. Here, we'll set up a container with a volume at /var/volume1. If we check it out, we can make a file in it. However, if we exit and run again, it will be gone. Volumes only exist until the container is removed. This might seem pointless, but now we'll see how these volumes are intended to be used. Docker volumes are meant to be shared and accessed across containers. If we run a data container, that is, one with a volume that runs detached like this, then we can create another container that attaches this volume using the ID or name of that container with the volume. We have the same volume mount as the first container, and when we make a file in it, it persists as long as the first container exists. Exiting and making another container that also attached the volumes from the first container will have the file we created. The first container becomes a means for a shareable volume to exist for other containers. When we come to clean it up, remember that this will also wipe out the volume and any data that was stored in it. Docker volume mounting is a very powerful feature and is necessary when working with stateful applications like databases, or for backups and log files. The next video goes on to look at ports and networking with Docker. See you there! In the last video, we saw how to work with data volumes. In this video, we'll explore ports and networking. Many containers are made for running services that you connect to. But when they listen on a port, it's not made accessible from the host machine unless you explicitly publish it. We're going to look at ways you can publish ports and then also talk about disabling the network altogether for extreme isolation. If a program is configured to listen on a port inside a container, it's not easy to know what ports we need to open. This is why Docker files have the expose instruction, which tells Docker what ports a container is going to want to expose access to. However, in order to actually access the ports inside the container, we have to explicitly publish these ports to the host system's network interface. The simplest way to do this is to use the -p option, which will publish all exposed ports. Let's do this with our Redis container as we've done before. Now if we look at Docker PS, we can see what ports it has and how they've been published. Docker will automatically pick a random port on the default interface to publish to. Another more programmatic friendly way to access information is with the docker port command. This command takes a container name or ID and then an internal port that's been exposed. Docker will then give us the interface and port it's actually listening on as the host. If a container exposed more than one port, we could do this for each port, although it would require us to know the internal port to look up. Let's clean up this container. In practice, the uppercase P option isn't used that often. Instead, we use the lowercase p option since it gives us more control over what is published and how. For example, here we can achieve that same result as before, but we can pick the port on the host to use. In this case, we choose to use the same port as the internal port. The format is public port : private port. We can also choose which IP to bind on. For example, to ensure this Redis server is only available from localhost, we can use the localhost IP 127.0.0.1 in the port spec. There it is running on localhost. All this port business is necessary because each container runs in its own isolated network, and Docker uses NAT to publish those ports. For outgoing connections, this is unnecessary, which is why we can connect easily to anything from inside the container. However, we can also prevent outgoing connections by disabling the networking for a container. We can do this by running with the -n option to set false. Now we can't even make outgoing connections. This can be useful for sandbox environments, but otherwise it's not often used. It's just an example of how you can configure networking for containers using Docker Run. As another example, you can also customize the DNS servers used by a container. By default, it uses the host DNS servers. But if you wanted to change that with Docker Run using --DNS equals 8.8.8.8, you could do so. Networking is another powerful component of Docker containers, and knowing how to publish ports is extremely useful, since many containers are made to run services. The next video illustrates how you can share ports in Docker in much the same way as we shared data volumes earlier. In the last video, we saw how to publish listening ports of a container. Similar to how we could share data volumes across containers, we can also share ports across containers so that they can communicate with each other. If you're running a Redis cache server in a container and want to let another container use it, you could publish it on the host's IP and then connect from another container via that IP. The problem is, you'd be exposing Redis on the public network. If we just want to let other containers talk to a Redis container, we can use a Docker feature called linking. Let's start by setting up a Redis server container that we can link from another container. We don't do anything different, except it's very useful to use a custom name for our container. Here, we'll call it Redis. Notice we didn't have to do any port publishing this time, as the Docker file has done it for us. Now let's create a container that will link to the Redis container. First, we'll need to do it with a container running bash, just to see what happens. The ---- link argument sets up a link. The value is going to be formatted as the name of the linked container, an internal alias for this container. So this container will refer to the Redis container link using the name db. We can see this if you inspect the environment. Linking will take any exposed ports of one container and make them directly accessible to another, and it will populate a number of environment variables for that container to discover how to connect to it, and add entries into the etc hosts file. All the variables starting with db, our link alias, will be related to that link. The most useful is probably db port, which specifies the address and port we can use to connect. Okay, now let's really use it. We're going to be using the Redis container to run the client linked to the server container and then connect using the environment variable. This time, we're using Redis as the alias and starting bash. We can see the environment is populated. Now we should be able to run the Redis CLI executable, and we're in. Linking makes inter-container communication very easy and safe. One drawback is that it only works for containers on the same host, and only for as long as the linked containers do not need restarting. In a future section, we'll see the common way to address this. In this section, we have covered Docker defaults, volumes, mounts, networking, and linking of Docker containers. In the next section, we examine creating our own application and shipping it to production. Welcome to this first video of Section 5. In this section, we're going to be building and deploying a simple web application using Docker. Although Docker is great for running background services and infrastructure, the real value comes from shipping your application. Unlike supporting infrastructure, your application will be updated and shipped quite frequently. Docker can make this process much easier. In order to demonstrate this, we're going to build a simple web application to deploy with Docker. We'll start in our Vagrant VM, and we're going to need to install a few packages. We're going to use Python in this example, but the example will be very simple, so you don't need Python experience. Really, this will be the same process with any language. Let's install Redis, Python, and pip, a Python package manager. Remember, we're installing these on our VM, not in a Docker container. Now with pip, we're going to install two Python libraries. The first is Flask, a web micro-framework. The second is PyRedis, which is a Redis client for Python. Now let's start our application. Create a directory for the project called Hello World. In this directory, we'll create and edit a hello.py file. I'm using the basic Flask Hello World example. You can see the source of this on the Flask homepage if you'd like to copy and paste. Now I'm going to save and quit with escape, WQ, enter. We can now run our app. In another terminal session in our VM, we can curl this URL. We can see it served our request, and we can close it now, Control-C. OK, we have Hello World, but let's make sure to include Redis in this example. We're going to edit our hello.py file and add a counter using Redis to maintain the state of the counter. By default, the client connects to the local host using the default port, but we're going to configure it now to try and look in the environment for a Docker link address. It will use the default for now, but later this will let us use Docker links. Right now, we just want to get this running outside a container. Again, save and quit with escape, WQ, enter. We'll run it again and open another terminal again. We can hit it a few times and see the container is incrementing with each request. That's our app. So we've made a very simple web application using Python and Redis. In the next video, we'll see how to put this inside a Docker container. In our last video, we've made a very simple web application using Python and Redis. Now, we're going to take this application and Dockerize it. With any application you build that you want to run with Docker, you need to Dockerize it. This just means to create a Docker container for it, usually using a Docker file. So we're going to set up a container for our application using a Docker file with a little help from the Make tool. First, we need to author a Docker file in our project directory. We start with the image we'll base it on. Let's use the latest Ubuntu. We specify a maintainer. Now, we install packages, so let's update apt-get first. Then, we'll install the same packages we did when we set up our application, except for Redis server. We aren't running that in this container. We'll stop here just to try it out. Make sure everything is installed properly. We'll run Python and just import the Redis module. It should return without error, and that means everything is right. Now we want to add our application source to the container. We'll do this with an add instruction in our Docker file. While we're here, we'll also expose port 8000 and add a default command so that it starts the app when we run the container. Since our build process includes our project name that we have to type all the time, we'll make it a little simpler by using a makefile. Makefiles lets you use the command to do simple project-related tasks. Originally for complicated build dependency processing, but we can use it for convenience. We'll make a build task. Now we can just run make and it will run the first task we defined, our build task. Our application is containerized with Dockerfile, and we also have the start of some nice project automation with Makerfile. Now we're ready to deploy this application container in our next video. In our last videos, we've put together a containerized web application. In this video, we're going to set up an application server to act as our production server to deploy to. Once you have an application container, you can run it locally just fine. But the whole point is to get it to also run on a server somewhere. It could be a production environment or testing environment on your own hardware, or cloud-based VMs. The point of Docker is that it can run containers consistently across all these environments. Let's make a simple cloud server to be our production environment. I'm going to use DigitalOcean to start a server because they're fast, cheap, and very easy to set up. I highly recommend them. You can get an account at digitalocean.com. Once you have an account, you can start up a server, or droplet as they call them, from the control panel. We'll name it prod and since it's basically a demo, we'll pick the smallest server size. One nice feature of DigitalOcean is they pre-build Docker images that already have Docker installed and ready to go, so I'll pick that under Applications. We used Vagrant for development because Docker only runs on Linux. We aren't using Vagrant on our web server because it is Linux. If you have an SSH key uploaded, this will make logging in very quick. If not, it will email you a root password that you will have to enter every time you log in. This will only take about 60 seconds and will have an IP we can SSH into. Okay, our server is up. Let's connect. We can grab the IP and paste it into our SSH command on the terminal. We can SSH from our VM or the host computer, or from directly through the DigitalOcean web page if you like. We'll check Docker is installed and up to date. Let's also pull the Ubuntu since we use this image a lot. This simply saves us a little time later. Lastly, since most everything we run will be in containers, we don't have to install anything else on this server. But let's pull and run the Redis container we've been using. Since we'll be linking to it, we don't need to expose any ports, and we'll just run it without a data volume for now. This should start a Redis server container. You can check the logs real quick to see. It's running, so we're done. Now we have everything set up on this DigitalOcean server needed to run our application, other than our application container. In the next video, we'll see how to ship our container to this server. In our last video, we prepared a server to deploy our Hello World web application. In this video, we're going to see how to effectively ship a container to another machine. We've already seen how to move container images across machines using Docker Hub. It turns out this is also the most effective way to ship containers around ourselves. However, we don't often want our application containers on the public index. Fortunately, we can easily run our own private index using the same software as the index, but running in a container on our server. Let's see how to set it up. The Docker authors have made a container application that contains the same application used to power the Docker Hub. It's called Docker Registry, and although they've made it quite configurable, the default configuration will do us just fine. Let's return to our DigitalOcean hosted server using SSH. This could be any server running Docker, but in our previous video, we set this one up to also run Redis, which we'll need for our application to work. First, we'll pull the Docker registry container. Now, we're going to run it exposing port 5000 and mounting a data volume that it will use to store images. This is important in case the application crashes. We can restart it and we won't have to re-push all our images. We'll just check the logs to see it's running. OK. We can now access our own private registry at this IP on port 5000. We're going to leave this session open and open another terminal back on our local Vagrant VM. We're already in our project directory, and we've also already built our application container, so it's ready to go. First, in order to push an image to a private repository, we have to tag the image with a new name that includes the address of registry. We can do that with the docker tag command. We're going to make a new tag from the Donald Simpson /Hello World app with the same name, except prepend with the address and port of our private registry. We do this because we use Docker push. It uses the name to determine if it needs to use another registry than the public index. But now we can just do a Docker push. Looks good. If we go back to our cloud server, we can now run Docker pull on that image name to get it from our registry and import it into our local Docker images. Now, for convenience, we'll re-tag it here without the registry name. In fact, because it's a private registry, We don't even need a username in our image name, but I usually keep it just as a good habit. Guess what? We can now run our application on the server in the same way we did on our local VM. However, we'll run it with a link associating the Redis container with it as the alias DB, as our app was set up to expect it. There it is running. We can grab the public port it's listening on from this output. Now, let's curl it. And again. And this is a public server, so let's curl it from our local VM. There it is. Our application deployed as a Docker container. We've done it, but we can do better. In our next video, we'll see how we can automate this workflow with a little bit of bash scripting. In our last video, we saw how to ship a container to a server using a private registry. In this video, we'll see how we can streamline the process and create an easy deployment workflow. Deploying isn't just getting your app on the server. You have to run it, stop any old versions, and, in practice, usually lots more. Although every app and deployment environment is different, we're going to see how we can use the pieces we have to create a single command deployment workflow. Most of the work in deploying has to be done on the server, so we'll start there. We're going to make a deploy script that will live in the home directory on that server. Let's log in, and then create a file called deploy-app. Now I'm going to copy this script in, but it's not very long and we'll walk through it. We'll start with the shebang line to say we want bash to execute this script. We also set -e so that if anything fails whilst it's running, the script will stop. We then set a few variables. The first is our public IP. You could hardcode this, but I curl the URL to get the public IP automatically. Then the first argument will be used for the name of the app, and the second for the version of the app. The name is just the image name, and the version is an image tag like v1 or v2. Our app is going to expose a port based on 8000 inside the container. And then we also need to set up the registry address. Now, the first thing we do is pull the app from the registry. We're piping the dev null to suppress the output. Then we run docker tag with the version information. Then we have this monster command that basically just looks for containers running with the app name and then does a forceful docker remove on them. Next, we start a new container that will be using the image we just pulled. Lastly, we look up the public port using docker port and then output this with the public IP. You shouldn't have to change anything in this script as it's fairly generic, but you can imagine how you might customize it to do more in a real-life situation. The script is designed to be run from SSH from our local machine. OK, let's save and quit. Then chmod this script with the execution bit. Now, back on our local VM, we're going to add our project makefile. We already have a build task, but now we'll make a deploy task. Then we'll make a new default task called all that will build and deploy. We have two variables at the top, one for version and one for the server's IP. We add a docker tag command to our build task. This gives us a local reference to this particular version once we built it. The meat is in the deploy task. It simply pushes our version tagged image. Then it runs our deploy script, passing it the app name and version. Pretty simple. Now we can simply run make and it will build our container image, then deploy it. At the end, it will give us an IP and port we can curl to test it out. See? And if we switch back to the server, we can see all containers running and see that it's running there. Here's the really cool part. If we add a version parameter to our make command, it will build and deploy a new version. For example, we can call this v1. Now it will have a record of v1. Let's change our app now and deploy as v2. We'll edit our hello.py file and change the hello world to hello easy deployments. Now we save that. And then we'll make v2. When it's done, we curl the address and see it deployed the new version. Since it has images of our old versions, we can actually run the deploy task without the build using an old version to roll back. There it is, the old code running, and you can see it's still using the same Redis data store. That concludes this section on deploying a web application with Docker. We now have a very simple system that in one command can build and deploy Docker containers, and in just another, roll back. You can see how quickly we can build up automation around Docker. Our next section will dive into this automation more thoroughly. In the previous section, we built and deployed a web application. We even scripted a simple deployment workflow. In this section, we're going to explore the idea of automation and tooling around Docker more in depth. The first step is to get familiar with the Docker Remote API. Docker was designed for automation and programmability. This command line interface that we've been using is actually a client that uses an HTTP API called the Remote API. By working with this API more directly, we can control Docker from a number of environments, not just the shell. Let's try using the API directly. Docker is normally configured to listen to a Unix socket, but we're going to use curl to interact with the API. So we need to modify Docker to also listen on a regular TCP port on localhost. If you're using the same Vagrant VM, we can make this change pretty quickly. Just open the /etc/init/docker.conf file using sudo and vi. We're going to add some flags to the way Docker is started. We're going to add a flag to listen on localhost port 4243. In production environments, it's important we only listen on the localhost IP, because otherwise it's possible anyone can connect and have full control of Docker. We also need to tell it to listen on the usual Unix socket, so we can also still access it the default way. Now we can restart Docker using the upstart, stop, and start commands. I will start the container too, which we will need for later. We can test that our change has worked by hitting the ping endpoint with curl. We should get back OK. Now let's check out the documentation for the Remote API. We can find it on the Docker Docs website under Command and API References, Docker Remote API. Then we pick up the latest version. It takes a few clicks to get to. This is the API. These docs show all the endpoints, example requests, and other information useful for HTTP APIs. We first want to list containers, which happens to be the first endpoint. It has a number of parameters, but we don't need to worry as they're all optional. Let's try it. Since I have a container running, it is described here in JSON. This is the same data that the command line tool gets when we run Docker PS. Let's look at a more complicated operation with the API. Start a container. The doc tells us exactly what operations happen and when we do a Docker run. In short, we create a container, then start the container. Optionally, we attach to it, but we'll just inspect the logs after. Let's look at the create container endpoint. This example shows a large JSON object we need to construct, but it turns out the only required fields are image and CMD. Let's put together a request with curl to create a container. This is a POST request, and it needs the container type of the application/JSON. Then we can specify the data payload. Since it will use double quotes, we quote this with single quotes, and then write a JSON object specifying the image and command we'll want to run. In this case, just echo hello world. But if we request write, it should respond with the ID of our new container. But it hasn't run yet. We need to start it. This is a different endpoint. We just need to post a sub-resource of the container using its ID called start. No parameters are necessary. To see the output, we can use the logs endpoint of this container resource. A quick check of the docs shows we need to specify a query parameter of stdout to get anything. So we'll add that. And there it shows our hello world echo output. Some of the API functionality gets tricky, for example attaching, which we can't properly do from curl alone. Luckily, in most cases, we can use a library that wraps this API in the language of our choice. Let's take a look at the Python library. Docker-py is a Python library for the Docker API maintained by the Docker authors. With some Googling, you should be able to find a library for your language of choice, but for convenience, we'll look at using this one. We should have Python and pip installed from previous videos, but if not, you can install python-pip with apt-get. Then we can just pip install docker-py. Now we'll change into the interactive Python shell to try this out. First, we import the module. Now we can create a client object. From here, we can use a number of functions that basically wrap the remote API. For example, we can easily list containers. We can also start a container with the same steps as before, but more conveniently in Python. First, we create a container. Then we start it. And we can check the logs. Most libraries will document their API quite well, giving you language idiomatic ways to work with more advanced aspects of the remote API. For example, we could have set the stream parameter to true, and it would have returned a Python generator to get logs back in real time with an interior interface. And that's the remote API. It's the basis for controlling Docker programmatically. Most of the time, you can just use the command line interface as we've been doing. However, if you're working with a non-bash environment, it would be a good idea to find a library of your language to work with the remote API directly. In the next video, we will look at ways in which we can expose this control to other containers. In our last video, we saw how to use the remote API to get programmatic control over Docker. In this video, we're going to see how we can expose this control to containers. By exposing the remote API to a container, we can make containers that automate some aspect of our Docker deployment. As containers, we can ship them around like any other Docker container. This also lets us delegate control to third-party containers that automate or extend Docker functionality in interesting ways. The most common way to expose Docker access to a container is to mount the Docker Unix socket inside the container. Here, we'll run bash in a container with the Unix socket mounted inside using the -v flag for setting up a volume. We'll put it in the same place as Docker would expect it. So now we have the host Docker socket inside the container. We just have to use it. To use it, we'll just install Docker. Since we're not going to run the Docker server, we don't have to worry about most of the dependencies Docker normally has to install. Instead, we can just install the binary directly using wget, which we do need to install. We'll just put the latest binary right into /user/bin and then set the executable bit. With the Docker binary and the Unix socket in place, we should be able to use Docker inside this container, as if we were on the host VM. Let's list the containers. We can even run a container and interact with it from inside this container. Now we're in a container from inside a container, though both containers are managed by the host VM's Docker daemon. Although running Docker daemon inside a container has its uses, for example, Docker itself is built this way, it's very rare that you'll need that level of isolation. However, sharing access to the host's Docker daemon by mounting the Docker Unix socket is much more common, as we'll see in the next few videos. In this video, we're going to apply what we've learned from the last video in order to run a utility inside a Docker container that arguments Docker functionality. Docker provides us access to container logs using the command line tool, but the logging world has specific protocols to ship log data around. I'm talking about syslog. Docker does not natively support syslog. If we wanted to use a log aggregator, we'd have to find a way to get logs out of Docker into the log aggregator. Luckily, there's a utility that does just that, and it runs entirely in Docker. The tool is called Logspout, an open source application created by Jeff Lindsay. If we run this container and give it access to our Docker Unix socket, it will attach itself to all the containers and gives us a nice way to both see those logs in real time as well as ship those logs somewhere else via syslog. Before I run Logspout, I'm going to create a few containers that will produce log output. This just means writing to stdout, since Docker only capture stdout and stderr. We'll do this with a simple bash script run inside a container. Here's what the output looks like. A stream of random numbers. We'll run a few of these. OK, now we run Logspout. We're going to run it with port 8000 published, and of course, with the Docker socket mounted, which Logspout wants mounted at /tmp/docker.sock. So we do that. We'll check the logs to see if it's running OK. All right, it's running. So, how do we use it? Well, the way to use it is to stream logs via its HTTP interface, which we published on port 8000. Let's see all the logs. You can see that it displays all of the output produced by the containers. It even color codes them and displays their name. We can actually drill in the stream logs for a particular container by name. What's nice about this compared to the regular docker logs command is that we can continue to stream logs across containers that run with the same name. For example, if you remove and create a container with the same name, you can keep this stream active. You can also look up by ID, but that's not particularly useful. There's also a filter endpoint, so you can see a subset of all the containers based on matching part of their container name. We'll stop Logspout for now. OK, though that's not the main reason we'd be using Logspout, we want to ship these logs to a log aggregator. For this example, we're going to use Papertrail. It's a simple web-based log aggregator with a free tier. It gives us a host and port to plug into something that speaks to syslog. Well, Logspout speaks syslog. Turns out, you can set up many routes in Logspout via a simple HTTP API, but the common use is a single catch-all route, which we can specify as an argument when we run the container. Let's run logspout again, without publishing the HTTP interface, but specifying the syslog address we got from Papertrail. OK, we'll see that it's running. And now, let's look at Papertrail. Looks good. It's streaming them in live, and Papertrail will keep a history of them we can sort through later. Logspout works with most log aggregators, so feel free to use something else. Logspout is an example of a Docker container that uses the remote API to effectively extend the functionality of Docker. In this case, it lets us ship container output to a remote log aggregator, as well as inspecting the logs directly in a number of ways. In the next video, we'll look at another more advanced tool we can run inside Docker. In the previous video, we saw how to manage logs using Logspout. In this video, we're going to be building our own Docker-powered mini-Heroku platform as a service using Dokku. The idea here is that we publish our changes to Git. Then they automatically get deployed. Most organizations that use Docker will have a process like this, as obviously nobody should be building Docker containers for production from their laptops. We're going to use a DigitalOcean droplet for this example, but you could set up Dokku on any host you like using the Bootstrap install script detailed on this page, github.com/progrium/Dokku. Just download the installer, set the Dokku_tag version, and run the Bootstrap script. To create our Dokku server, we will return to DigitalOcean and set the host name, size, and location we want for our new droplet. Once that's done, we browse the available applications and select Dokku. The final step before creating our new image is to add in our SSH keys. I have already got mine added. But if you need to add yours, you can do so as the vagrant user. Just cat the id_rsa.pub file and add that to the DigitalOcean page. Adding SSH keys is not essential, but it makes life easier and will save you time in the long run. Once we're ready to go, it should take about 1 minute for the Dokku DigitalOcean droplet to be created. Stop here for the server to build. OK, that's the new server ready, and we can see its IP address here. If you added SSH keys, you will be able to log in directly now. And if not, you will need to wait for the email details that contains the new password. The host is available and we can connect to it OK. While we're here on the Vagrant VM, I will also set up SSH keys for the Dokku user using this command. Note the IP address of the new droplet there. If you point a web browser to the IP address of the droplet, you will see the Dokku setup page. If you are setting this up for permanent service, you could specify a domain name here, but we're simply using the IP address for this example. OK, that's our Dokku host set up and checked out. The Dokku user is available to connect via SSH. So we should now be able to deploy it. What we need is an example application to deploy. Let's pull the Node.js example project for this. Stop here. OK. Now we add git remote, specifying our remote Dokku server and the name of this project. Now we simply do a simple git push to that remote, and the application will build and installed on our remote Dokku host. Once this process completes, browse to the host IP at the port specified in the output, and you should see the newly pushed application running on our Dokku host. In this video, we saw how to build and run a Heroku-style PaaS in Docker using Dokku. In the next video, we are going to take a look at some other interesting Docker patterns. In the previous video, we took a look at using Docker to build our own platform as a service with Docker. In this video, we'll be looking at Docker pattern called ambassador pattern. An ambassador is a container that acts as a local agent for a remote container, and here we're going to see this in action with Redis. Docker links let a container find and connect to a service running in another container, but this doesn't work across hosts. The ambassador pattern was developed to solve this. An ambassador is any container that acts as an agent for a remote container, letting you use Docker links between your container and the ambassador, resulting in a link with a remote container. Ambassadors are basically proxies. To illustrate, we'll set up an ambassador locally on our Vagrant VM and a Redis server on a remote DigitalOcean VM and connect the two containers using an ambassador. For the server, we'll use a DigitalOcean droplet running the Docker application under Ubuntu. On this host, we'll start up a Redis server as usual. We will name it Redis. Now we run an ambassador container. It's a very simple container, but it's designed to proxy based on the links provided. Here we will link it to the Redis container, which will set up what it proxies to. We also expose the Redis port from it, so we can also link to it. This completes our server configuration. Our Redis application and ambassador are both running. Back on our Vagrant VM, we start up an ambassador container with Redis port 6379 proxied to the DigitalOcean droplet where Redis is running. With that running, we should be able to connect a client container through this ambassador. This ambassador connects to the ambassador running on the remote DigitalOcean machine, which then connects to the Redis server container. There it is. We're connected to our container running on DigitalOcean. And both the client and the server were set up with the assumption of links. We just had to set up ambassadors to connect them up. Ambassadors are a powerful pattern. You can find many flavors of pre-built ambassadors. Some are dynamic. Some use various server discovery technologies. The idea is the same. And of course, you can always build your own ambassador containers as they're effectively just reverse proxies. In this video, we looked at ambassador containers and seen them in action. This brings us to the end of the course. Well done on getting through it, and I hope you have both learned from and enjoyed it. Our Docker journey started with an introduction to the basics, then demonstrated the key commands you need to know. We then covered some practical examples that put our learning into practice, built our own application, then packaged and deployed it. We finished off with a look at creating our own PaaS and one of the more advanced container patterns and possibilities. If you would like to find out more about any of the topics we have covered in this course, there are many useful resources online. There are a few useful examples on the screen.